Um, Welcome all of you on the presentation. So I will talk on the edge computing for AI. So it's a system research needed for running AI models and ML models on the devices and on the edge computing. I will lead this theme together with Blesson Varghese from St. Andrews University, and the universities taking involved in this research are, of course, Newcastle, St. Andrews, Southampton, University of West Scotland, and Imperial College London. So we'll try to work on the edge computing for AI. Typical AI for the cloud is defined by the unified unlimited resources, large neural networks and large models, and the terabytes of data that are processed by these models. In contrast, in the edge environment, we are mostly working with streams of data from the sensors, from the cameras. We need to deal with low power networks, like narrowband IoT or some Bluetooth mesh networks, or for example, LoRaWAN networks. And of course, we need to think of low power and optimized models that we can deploy on the devices. And of course, the most important aspect is that these algorithms and the data needs to be processed on by the low power devices, as we have on the slide. So it can be some small sensors like accelerometers, or the pressure sensors with some processing units inside. Then we might think of some microcontrollers, like in the Arduino board. Then we have bigger devices with more resources, like Raspberry Pis and NVIDIA Jetson Nano, Orin, and this kind of devices with embedded small graphic GPUs for processing the data. And finally, we might have the low power edge clusters for processing the data, for example, in the factories, without the necessity to send them to the cloud. Nevertheless, in the case of low power devices, we have silicon limitations of the processors inside, which makes them suitable for processing different types of data. So for example, on the low power sensors, the accelerometers one, the sensor itself, we can only process the time series data, for example, for predictive maintenance of industrial devices. Then on the small microcontrollers with floating point processing units, we might think of analyzing the audio data, for example, for keyword spotting and detecting some keywords in the field. Then on the small Linux-based systems, we might think of object detection, for example, for security applications. And finally, for the small clusters, we might think of video processing, like surveillance cameras or some quality assurance, vision quality assurance in the factories. So what we need to think of the limitations that these devices have and how to deal with this kind of devices deployed in the field. So in this research theme, we are focusing how to prepare, deploy, and run the models on the devices, and how to make the end-to-end system based on of devices and how to and the data processed by them. So we have analyzed the typical ML ops paradigm and the application for Edge AI, and we have identified few problems that we need to work on in this research theme. First of all is the problem related to training on the devices. So the training is resource and processor and the memory intensive. So on-device training is usually not possible. So we need to think of some sort of way how to train the models in different way than that nowadays used for cloud systems. Then we have a problem with heterogeneous devices and the number of coprocessors and the extensions to the microcontrollers that are developed for supporting processing the neural networks. So we need to think of how to optimize the models for the hardware and how we can utilize the hardware extensions that we have in the processors. And finally, after deploying the models in the field, we needs to find some ways how we can control and observe how the model behaves, how the device behaves, and what is the difference in the data quality processed by the models, and if the model still behaves well after deployment in the field, in the changing environment and changing context in which devices needs to operate. So to sum up the previous slides, edge computing systems are quite complex because they are composed of different types of devices. They have limited resources, they have different types of hardware. We have several ML tools and techniques on the market targeted for these kind of devices. We have problems with limited and intermittent communications. So it makes it quite hard to deploy ML models and to assure that they are working well. So our aim in this research team is to simplify the training and deployment of complex ML models. We thinking how to simplify the execution of these models on different types of devices and how to make these models adaptive to the changing execution conditions, to the context in which the devices operate. So therefore, at the end of the day, we would like to propose some new tools and techniques to help practitioners to achieve these goals, to optimize and to simplify the process of creating, deploying, and observing how the model behaves on the devices. So therefore, we have identified a few research areas. First one is the new ML training paradigms for edge devices. So we are thinking how to improve the training process on such devices and what are the benefits of the techniques that we are going to develop. Then how to enable on-demand rapid ML deployment on the edge, how we can optimize and reduce ML models before deployments to the edge. And we are not talking about the model quantization and the typical techniques like the running or quantization of the neural networks. But also we are thinking how we can reduce the footprint, the memory footprint of the models before sending these models to the devices, just to limit the network consumption and the network utilization for these devices. So it's simply the very technical engineering work to do, but it's still the research problem. So then we are thinking how we can reduce the communication needed for the collaborative training on the devices, because we are talking about the IoT systems, distributed systems. So we are talking about the devices which can send the information between themselves. So we need to reduce the amount of information sent between the devices for the training purposes. And finally, we'll work on the ML model observability and how to monitor model quality over the time after the deployment. It's the research related to what Varun presented before regarding the data quality detectors and the model quality detectors. We have some results in these areas. We have some prior experience and the know-how how to design such systems. So first, regarding the new training paradigms, we think that on-device training is very challenging, but typically used the backpropagation algorithm is which is quite old, well established, but it's insufficient for the edge computing devices and IoT devices because it's memory and compute intensive. And of course, it limits the training possibilities on the devices. So therefore, we are thinking of more robust and adaptive techniques, one of which is the NeuroFlux, developed by one of our universities being a part of the hub. So the idea is just to adapt the size of the training batches on the devices based on the resources available on the devices in order to reduce the memory consumption and the time needed for training the data. So some results have been presented on the conferences and in the journal papers of these solutions. Then we have some, we observe, due to our experience and our test bench, we are observing increased interest in the mesh networking protocols, especially for smart homes and smart cities. So based on our experience, we would like to utilize this kind of communication mesh communication between the devices for exchanging the knowledge between the devices and between the ML models deployed on these devices, because we see it as a promising new area of research. So we have some experience of some distributed and collaborative anomaly detection for the industrial machines. And we would like to provide some tools and techniques for in this research area. And finally, based on our experience in developing IoT systems, we have observed some significant percent of IoT project fails, mostly due to the changing conditions in the operation of the devices, how the devices work, how the context in which our devices operate to change, and so on and so forth. It all causes the IoT systems mostly to fail. So we think that this is the same problem for DynML models and ML models deployed on the devices. So therefore, we are working on the tools and techniques for model observability. We would like to provide some tools to provide the answer to such a question like what input data caused the highest anomaly score in the last 5 minutes, just to inform the owners of the system what is happening in the system, what causes some problems in the system, and what is the model input data distribution, how it differs from the training data set, and what is the data quality models. This research will be connected to what Varun presented before regarding the data quality models and the quality assurance. But we would like to run these detectors on the IoT devices, on the microcontrollers. So we have a number of research problems, how to optimize these models and how to pick the most sufficient algorithms for data quality detectors that could be deployed on the sensors, microcontrollers, and the Linux-based system. And finally, to sum up this research theme, we are observing the emerging research challenges. We need to support the new generation of the hardware. We need to think of new kind of silicon and the processing types like non-von Neumann processing, non-von Neumann processing, neuromorphic hardware, and the other advances in this field. We see the huge problems with deployment and management of IoT devices and the models on these devices. So we are working on handling these problems. And of course, we would like to see more low power communication protocols and interfaces for the DynML in the DynML domain. And of course, for it, we need some strong collaboration with the industry. We are welcome some suggestions from the industry. What are the main challenges and opportunities with deployment of systems that you have, and what specific actions you would like us to perform in order to help you to solve your problems. So it was a short presentation of research tasks that we are planning to do in the research team related to edge computing for AI.